This lesson will start to answer the question, what is a force and how can we analyse combinations of forces? Over a few centuries of careful observation, experiment and mathematical modelling, physicists have come to understand that there are four fundamental forces in nature that explain most of what we can observe: the gravitational force, the electromagnetic force, and the strong and weak nuclear forces. And notice how I said most just then. Something we don't yet understand is the force that's causing an accelerated expansion of the universe. But back to our everyday world, and you have probably heard people refer to many different forces, such as magnetism, friction, drag, and buoyancy. It turns out that most of these forces are actually different manifestations of either gravitational or electromagnetic forces. But what do we really mean by a force? Quite simply, forces are what cause changes in motion, either in direction or in speed. So force is a vector quantity and it's related to acceleration. Now if I throw a tennis ball and then I throw a shot put using the same amount of force, the tennis ball is going to accelerate more than the shot put. This is because the shot put has more mass. And so mass is what determines how much acceleration happens to an object when a force is exerted on it. This is neatly summarized in Newton's second law, F equals ma. This little formula is one of the truly amazing discoveries of science, and it's remarkable because it is so simple and yet so widely applicable. Everything from minute particles to planets in the solar system moves according to this relationship. The second key thing you have to remember about forces is that a force is always the result of an interaction between two objects. So we should always be able to identify a force as the force due to A acting on B. It's also important to realize that a force is not an intrinsic property of a single object. It cannot be stored or used up like energy can. Mass is an intrinsic property of the object, but the forces and acceleration it might experience depend on the circumstances it is in. And by that I mean what other objects it is interacting with. Let's look at gravitational forces in a bit more detail. One of Newton's great achievements was to show with rigorous mathematical calculations that the gravitational force between the Sun and the planets in our solar system, which are large spherical masses, is exactly the same as if the mass of each planet were concentrated at its center and directed along the line between the center of the planet and the center of the Sun. For two such spherical bodies, such as the Sun and Mars, the gravitational force exerted by one on the other is given by this formula here. Ma and Mb are the masses, Rab is the distance between the centers, and the quantity g is called the universal gravitational constant, as it's assumed to have the same value anywhere in the universe. So if we could move Mars so that it was twice as far away from the Sun as it is now, it would experience a force that is just 1/4 of what it does now. And so this formula is called the inverse square law. Another of Newton's great insights was that exactly the same type of forces exist between the Earth and an apple falling off a tree. So the gravitational force exerted by the Earth on the apple acts as if it points from the center of the apple to the center of the Earth. Now when we move an apple around, we barely ever change its distance from the center of the Earth. Even if we take it from sea level all the way up to the top of a mountain, this change in elevation is just tiny compared to the radius of the Earth. So for most calculations of gravity near the Earth's surface, we treat the distance REA from the center of the Earth to the center of the object, we treat this as a constant. And that means we can combine these three terms here into a new constant called little g, or the acceleration due to gravity. And this has the value 9.8 meters per second to two significant figures all over the Earth's surface. Every single object near the Earth has this force acting on it, and it always points down towards the Earth's center. It's what we experience as weight. Now this is a good point to pause and talk about the difference between mass and weight. Mass is the quantity of matter, and it tells us how much resistance the object has to changing its speed. Weight is the force a small object experiences due to the gravitational interaction with a very large object, such as a planet. And the reason people confuse weight with mass in everyday language is because of this relationship, F equals little g times m. and this little g is a constant in everyday experience. So weight is proportional to mass, but they are not the same thing.